Hello everyone, in this video we'll learn how to estimate vector autoregression model in panel data. So in this tutorial we will need three packages. The first package is panelvar. You can get it from the CRAN repository. Just go to packages and click install. And the second package is PLM, panel linear model. This package can define our data as panel data, this line, index, ID, and year. And the third package is for Excel, to read Excel files. So before we start coding in R, we should take a look at the package. The package called panelvar for panel vector autoregression models, developed by Michael Sigmund and Robert Fertzel. So this package is for general methods of moment estimator to panel vector and strictly exogenous variable. This general panelvar model contains the first difference GMM estimator. It means that this package you can estimate a VAR model with the difference GMM, and the system GMM estimator provide also Hansen test for over identification and the lag selection criterion and the stability test of the panelvar model, and classical structural analysis for panelvar models such as orthogonal and generalized impulse response functions, bootstrapped confidence interval for impulse response analysis, and forecast error variance decomposition. So in this package you can estimate model using GMM estimator, and and for fixed effect estimator, so and can coincidence estimator. So we have three types of estimators: GMM and this fixed effect and Klein. I also have this paper of the same authors, Michael Sigmund. In this paper, he conducts a comparison between the Stata and R packages to estimate panelvar model. So I will leave all these papers down in the description. Also, should take a look at our data. So I'm always using synthetic data. I have this panel data time span from 2004 to 2015, and I have 12 region. This is Morocco region. This is it. So, as you see, we have 12 region, and I have four variable 1, variable 2, 3, and 4. For the third variable, it's I don't have all the data, so we are in the unbalanced data. So this package handle also the unbalanced data. It means that you can estimate model for balanced and unbalanced data. So I should mention also that the literature for estimating VAR model, you should have stationary variable. It means you should conduct stationarity test for this 4 variables. If you look in my channel, you will see that I have already a video talk about stationarity test for panel data, and you should see this video and try to to fix the problem of stationarity of a variable to have a stable model, stable VAR model. So I will suppose that my data is already stationary, and now we go to have already installed these three packages. So I start by uploading my libraries. PNM. Now loading my synthetic data. I changed the path, so we can do this manually to see the steps in my computer. After I upload my data, I move now to rename my data and to define my data as panel data using the PLN package. And this is my identifier for individual and time, like my data. This is the identifier. I have 12 region. For the data, in this data, you should the individual identifier should be numeric and it doesn't handle with the string data. So this is my my data set. We can take a look at the data in the R editor. So this is my data. As you see, I have a missing value here, and that doesn't after defining my data as panel data, as I said in the VAR literature, before you estimate a VAR model, you need to define the lag. Yes, you need to define the lag. I start first by choosing lag 1. Or first, I should define this line. So I start first by the first line here, the dependent variables. I choose just 3 dependent variables. Like I said, we should define each line of this code. So the first line is dependent variables equal column of variable 1, variable 2, variable 3. So this is my dependent variable to be estimated for our VAR model. The second line is lag for the dependent variable. So when I choose lag 1, it's for the dependent variable, or lag2 or lag3. So in my case, I choose lag1. And the third line is the predetermined variable. It depends on the exogenous variables. It depends on your paper, on your problematic. If you find that the literature said that, for example, the variable 1 is defined as predetermined variable, so you put it here in this choice for dependent variable. And also the same idea for the exogenous variables. In my case, I just choose this variable 2 and 3 or 4 as the exogenous variable. It just to try to simplify this code and to show you all the possibility for this error code. And this transformation is for to define the type of the transformation. In this case, as you see, this option is for transformation of instruments. If you want to choose first difference, just type FD for first difference, or forward orthogonal deviations, type FOD. Instrument, if you want to use instruments for orthogonal deviation equation, choose FOD. And the next line is for the data. As you see, I already defined my data as panel data. I choose the name dataset, so the data is dataset is here. And the second line is for panel identifier. As you see, I have the ID as the individual identifier, and year as the time identifier. Take a look at my data. This is my time identifier or time group, and this is my ID. You could choose this ID here or this ID N. Instead, you can choose this option for the strength identifier. Second line is for steps. As you know, in the GMM, you can use the first or one step, or the second or the two steps, or iteration, as you see here. As you see here, the choice of the steps, you can choose one step GMM estimator, or two-step GMM estimator, or M-step GMM estimator. M-step is for iteration, mini or M iterated efficient of GMM estimator. The one step and two steps, the two steps will give the good options. And also this M steps, for this M step you can conduct optimization, and we will see this in this code, the part of optimization. Next line is for the system GMM or GMM on difference. If you choose system instrument equal true, which means that you want to estimate this VAR model using system GMM. And if it falls here, you write false here, false, it means that you are choosing a VAR model using GMM indifference. And moving now to this PCI instrument. PCI is for Principal Component Analysis instrument. As I said, the system instrument, if it's true, it means you want to use the system GMA, and the PCI instruments, if it's true, that you mean you want to use PCI instruments matrix. And this for this I think 4 line maximum instruments for the dependent variable, I choose 16. It means that the maximum number of instruments you use for the dependent variables. Dependent variable, in my dependent variable is this variable 1, variable 2, and variable 3. And the next is for the maximum number of instruments for the predetermined variables, 16. This is my predetermined variable, is variable 1. And this 2 line is for the minimum number of instruments for the dependent variable. I choose 2 to use the minimum number is 2. And the minimum number instrument for the predetermined variable. There is also another option in the this is another options for the exogenous variable. For the predetermined variable, I choose to use minimum as 1 lakh, and the last option is for the collapse option. If true, it means that I want to use the collapse option. As you see in this picture or the snapshot, Bootstrap IRF impulse response function uses blockwise sampling of individuals using the bootstrapping method for panelvar. We have this option type of IRF. IRF is impulse response function. We have 2 options. It can be orthogonal impulse response function or generalized impulse response function. It depends on your work or in your paper or in your empirical review. And we have the number ahead, numeric number of steps. You can use 6 or 7 or 9, or it depends on your results. And we have here the number of draws in the output. And the last thing, we have the confidence bound. So we're back now to the R to see the result. As you see the results after calculating the impulse response function. Now we can take a look at the forecast error variance decomposition. We will see this results after in the plot option. Now we can also take a look at the forecast error variance decomposition for panelvar. For the variable 2, variable 3, variable 1. I choose forecasting for the 10 period ahead or for the next period. We can modify this. So for example, I choose 20 and see the result. This is the result of 20 Now, generalized impulse response function. Now we will see plot here. There is generalized and there is another option for orthogonal. We will see this. For example, we see the generalized. Now we plot the graphs. And this is our generalized impulse response. Using this option, we have 6 ahead and approximately 8 steps. And then now for the orthogonal impulse response function, the same options. Now we want this, for example, in this we plot, for example, the orthogonal and the orthogonal impulse response with this the p-var, or the empirical estimation of the p-var impulse response. This output here included here in this option to plot the confidence response. As you see, my results have no sense because I'm using synthetic data. Now you can take a look at the stability of this p-var model. We conduct the stability for this model. Now we print the results. If you want numerical result, this is the eigenvalue and the modulus. As you see, there is not all the eigenvalue lie inside the unit circle. You can see this sentence as I show here. As you see, for the p-var to be stable, we need to see all the eigenvalue inside this circle. If all the eigenvalue is inside this circle, it means that your VAR model is stable. As you see, not all my variable is inside this circle. It means that not stable. Now, as you see, of course, the results is changing if I change this log value. For example, I choose log 3 and do the same steps. This is the output for using log 3. And now the enhancing test. This can take time. I changed the log to log 3, and you can play with this option. For example, this and this option to have a good model. Of course, with respecting the test of these options. That can take time. Sometimes take 30 minutes or less. I will stop the video until I have the output. As you see, the convergence is finished. Now we can see the results. Not the result for forecasting, and now the generalized universe. So we change the lag just to show you that the lags is impacting the model and impacting the results on the results. The result of the model. I hope this video will help you to have a look and to estimate your own VAR model for panel data, and you can find this code and also this package on this paper for the author of this, the two author of this package, panelvar. As you can see in this paper, he's conducting estimation using this same package and comparing the results with the data package called I think called the VAR. Yes, it's called VAR package in data, and he is comparing between these packages results and and giving some detail about the output and the methodology used for estimation. And also you will find all the mathematical behind this estimation. Also, this is Windmeyer correction. And now it compares between the data package VAR and the panelvar estimation. This is the function that we used, panelvar GML, and comparing the results between these two outputs. So I hope this video will help you to estimate the model. You will find this code and also this synthetic data to simulate this video. So I hope this will help you, and if you like my videos, please subscribe and hit like to see more videos.